you are welcome back to Introductory Mathematical Analysis A. We are still in chapter 1 now, as in chapter 1. But now we are going to enter into section 1.6. 1.6. All right, in 1.6, we are going to be dealing with sequences. All right. For n, a positive integer, a sequence of length n is a rule that assigns to each element of the set 1, 2, 3 up to n exactly one real number. Okay, so that set 1, 2, 3 up to n is called the domain of the sequence of length n. And because it ends at n, that is what we call a finite sequence. That is what we call a finite sequence. Okay, so a finite sequence is a sequence that has 1, 2, 3, and then these 3 dots. Remember, we mentioned that in the previous video. Then n. Okay, when you end at n, then that is the last one, and this is a finite sequence. A finite sequence. So, but we also have what we call infinite sequence. In infinite sequence, there's no ending at n, so you have only those 3 dots with it. Okay, so when you put only these 3 dots, don't forget it's just 3. It's not less than 3, it's not more than 3. It's 3 dots to show that these values we are writing continues. Okay, it continues. All right, so we have finite sequence that ends as a number, in this case n. We have infinite sequence that we don't have the n there. All right, please take note. Okay, so let's take some example of sequences. Let's take some example. Okay, in the first one, if we have AK, k equals to 1 to infinity. Okay, k equals to 1 to infinity. And you will notice that in the sequence, we don't have addition. We are not adding them together. Okay, they're just items on their own. Okay, so this one now, this sequence of this, we don't know what is AK, so AK is defined for us as this. Okay, this is AK 2k squared plus 3k plus 1, that is AK. Now if you want to put this into that sequence, we are starting from 1 to infinity. When k is 1, what will be? This will now be A1. What will be A1? You put 1 there. 2 plus 3 plus 1, that is 6. A2, you put 2 there. When k is 2, you put 2 there. Then this will be 15. A3, when k is 3, you put 3 there. So this can actually be written as this, since we say AK is this. So we have 2k squared plus 3k plus 1, k equals to 1 to infinity. Okay, you can have that. Okay, so now A3 will be 28. All right, we can stop there. We can also have A4. So this sequence, the sequence is 6, 15, 28, but because it goes to infinity, then we have our 3 dots. Yeah, it goes to infinity. Okay, so that is the sequence represented by this. Okay, now let's go to another one. We want to deal with the sequence represented by this is an infinite sequence. So I can write it as this. So the infinite sequence of EK k equals to 1 to infinity also. It's an infinite, infinite sequence. Okay, but the ek is defined by this. The ek is defined by this. So again, let's find our e1. E1 is simply putting our k equals to 1 there. So k equals to 1, that will be 2 over 1, which will be 2. Raised to power k again, raised to power 1. Okay, which is still 2. Okay, 1, 2 raised to power 1 is still 2. Then E2 will be what? 2 plus this, that is 3 over 2. Then raised to power 2 again, raised to power 2. Okay, so we have, this is 9 over 4. Of course, E3 follow the same pattern, which is 64 over 24, over 27 rather. Okay, E4 follow the same pattern, E4, which is this now. So we are just following the sequence defined for us. So we list 4 terms of it. We list four terms of it. So this is 6 over 256. All right, you just list 4 terms, and then the sequence is now the infinite sequence. The infinite sequence, we have 2, 9 over 4, 64 over 27 over 256. Then we put our 3 to show it continuous. Okay, please ensure you understand. Okay, again, we want to write out this as a compact sequence formula or form like this. Okay, we want to write it in this form. Okay, we want to write it to define our AK. All right, in order to do so, you must be sure of this is 41. 41. The next one is what? 44. The next one is 47. What is the difference? Is 3. Okay, the difference between them is 3. Okay, so, and we want to count from k equals to 1. So that means we can write as this k41 plus k minus 1 multiplied by 3. Okay, multiplied by 3. So that means if k is 1, this will be 0, so it will remain 41. If k is 2, this will be 2 minus 1, which is 1, multiplied by 3, 3. Then 3 plus 41, 3 plus 41 will be 44. Okay, so this formula will work. So we can define our AK to be, I can even open that up, 41 plus 3 into k minus 1. Okay, if I open this up, I will get 41 plus 3k minus 3. Okay, so this is same thing as, this is 41 minus, that is 38 plus, okay, that is that. So I can actually use this, or I use this, or I use this. Okay, you must make sure you test and see that each of them gives you each of the terms in the sequence. Okay, so we can define now our AK to be this, and it will be counting from 1 to 5, and it will give us all of this one. Okay, please make sure that you understand how to do that. Again, if you want to write this in this form, and this is supposed to be from k equals to 1 to infinity. Okay, from k equals to 1 to infinity, and then want to write it in that form. Okay, now if you look at this one, this is 1, 1, 4, 9, 16. Okay, and they don't have any term like this one that is the difference. So this is just 1 raised to power 1. This is or 1 raised to power 2, but let's go with this one. This one will be 2 raised to power 2, am I right? So that means this is supposed to be 1 raised to power 2, and then this will be 3 raised to power 2, and this will be 4 raised to power 2. Okay, so it's just the square of each of the term. Okay. All right, so it's just the square of each of the terms. So if we are going from 1 to infinity, we just have that we can now define our AK. I can define my AK as k raised to power 2. K raised to power 2. I can define this as k raised to power 2 because when k is 1, then this is 1 raised to power 2. When k is 2, 2 raised to power 2. When k is 3, raised to power 2. When k is 4, 4 raised to power 2. When k is 5, 5 raised to power 2, like that. So our AK in this one, in this example, is k raised to power 2. K raised to power 2. All right. Of course, we can also define the term in this way, but just go with this simple term here. Okay, so an infinite sequence cannot be determined by finitely many values. Cannot be determined by finitely many values. Okay. Now we come to another sequence. Sometimes a sequence is defined by the time of itself. Okay, by the terms of itself. Okay, that sequence that is defined by the terms of itself is what we call recursively defined sequence. Recursively defined sequence. An example of such sequence is Fibonacci sequence. Fibonacci sequence. This Fibonacci sequence is defined by this. Is defined by this. Okay, this is a Fibonacci sequence, or you can write it this way also. Okay, this is also a Fibonacci sequence. You can write it like this way. Or you can even write the whole thing inside, and then you get 0 on the other side. Okay, so but mainly we do write it like this because we have a value here. We need the sum of these two other smaller one to get this one. Okay, so and because we have now k plus 2, we need the value of so for example, now if k is 0, then that we are going to be beginning this Fibonacci sequence at 2. So that means I'm going to have something like this: k plus 2, I write it again, k plus 1 plus f of k. Okay, so if k is 0, okay, that means we are going to have k2 equals to k1 plus k0. So I need k0 and I need f of 0 and I need f of 1. Alright, but if I'm counting k from 1, if I'm counting k from 1, if k is 1, then I will have f of 3 equals to f of 2 plus f of 1. So at start, I need f1. At the beginning, I need f1 and f2. So you are going to be given what is f1 and f2, and then you can find your f3, and then continue with it to find f4, to find f5, to find f6, and like that, okay? All right. So in this case, if you are given f1 equals to 1 and f2 equals to 1, f1 equals to 1 and f2 equals to 1, so we get this term, f1 is 1, this is f1, this is F2, this is F3, this is F4, and like that up to F10. Okay, so that is the first time, the first 10 terms of this Fibonacci sequence. All right. Okay, so don't forget this type of sequence is called recursively defined sequence. All right, so now we come to arithmetic sequence. Arithmetic sequence. Okay, so this arithmetic sequence is also recursively defined. Okay, recursively defined for each positive integer k. So we can have our arithmetic sequence as this plus b of k. Okay, so we have bk plus 1 equals d plus bk. All right, we can also write it like this, equals to d. So that means the difference between the term and its next term, the next term to it is the difference, okay? So, and this is what we call the common difference of the arithmetic sequence. So like the example we had before, we just find the difference. What is it? Because they have a difference. So like this, in this example, they have a difference. So we just find the difference and we use the difference, okay, in order to get the formula for the sequence. Okay, so in this one, the 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 difference between the term and its next term is a difference which we need to use to find the formula whenever you are asked to find the formula of it. Okay, so for example now, let's write explicitly the terms of an arithmetic sequence of length 6 with the first term to be given as a equals to 1.5 and the common difference to be given as this. Okay, so we have this. If we have bk plus 1 equals to d plus bk. Okay, so this bk is also the same thing as a. Okay, it's also the same thing as a. So if I want b1, when k is 1, that means now b2 will now become d plus b1. And this b1 is our a, d plus a. Okay, so b1 is given 1.5, which is a. Then b2 will now be the difference, 0.7 plus our a, 1.5. Okay, and of course, the sum is given as this. Okay, that is our b2. We can use that again to find our b3. Is still the difference, the difference, the common difference, plus our b2 which we got here, which is 2.2. So we add it together, we get 2.9. So we continue like that. We get b4, b5, b6. We are asked to find 6 of length 6. Okay, so you could be asked to find length 8 or length 9 or length 10. You just continue like that up to the length you are asked to find. Okay, up to the length you are asked to find. All right. Okay, I hope you understand. Please ensure that you understand.